Beautiful. All right, we're live. So hi, this is the Composites for Interiors. It's nothing really too interior specific about composites, but I know a lot of the interiors team members uh, had plans to use composites in their parts in some way or form. So this was a good kind of introduction, I thought, for all of interiors to get on the same page. So we'll see how long we take. Hopefully we're fast. Otherwise we might be about half an hour. That's what I planned it for. So we're going to be covering hopefully just like a bit of an overview of what are composites, how do we manufacture them and make them, and a bit about the tooling and molds. And oh yeah, happy Canada Day. I shared this photo at random, but I took this photo 2 years ago. I thought it was kind of funny. We were like packing up for ASC and there's Canada Day fireworks in the background. So yeah, it's been officially 2 years. Anyhow, so I want to get everyone acquainted with at least composites, what they are, I guess, how we use them on the team. I did steal some slides from Jason, so he did a great job for putting his slide deck together. But I do want to talk about like the different composite materials, some of like the different properties, their limitations, how we manufacture with them. I've also included some links about learning more. And I will share the slides just in the various Slack channels after if you want to kind of look through this yourself. But diving right into it. So I guess like what are composites in general? I guess online you can read through the definition, but it's just essentially multiple materials put together that have different properties. So some examples, they aren't necessarily always like carbon fiber or fiberglass. Some of the most common ones are all around us, like concrete or plywood. Paper mache is actually a really good example of composites, or like foam core board. So all these, they use different materials. Like concrete is typically the concrete or the cement plus whatever aggregate or rebar, and those all come together to make a much stronger final product than their original constituents. So from a kind of traditional, what we use is something called fiber reinforced plastics, or FRPs, and they are just what they sound like. So you have some sort of plastic, and it's reinforced with fibers. So normally we see a lot of fiberglass and a lot of carbon fiber, but some of the ones you don't look at as much that also exist are Kevlar and hemp even. So in general, it's just the plastic, or yeah, there's some sort of plastic, and you're strengthening it by adding fibers. So when and like why do we even use them? So I just Googled this and like this came up. But you can see often it's like you'll see aerospace, you'll see marine or automotive. And typically it's all for the same properties, where you've got, I guess, a lightweight material with a really high strength to weight ratio. So it's really strong, but doesn't weigh a lot. But you can also form it into rather complex shapes. And that's one benefit that gets overlooked a lot, is yes, we know they're light, and they are fairly strong overall. But some of the shapes, like if you're looking back at like a wind turbine blade, for example, trying to make that out of, I don't know, sheet metal or titanium or something, let's say, may actually be a lot more work than it would be to do with composites. And that's part of the reason why we use them on this team. So in general, with any fiber reinforced plastic, you have a fiber, you have a matrix, or your plastic normally, and together they make a composite. And it's the same terminology used for any composite, where you have some sort of fiber. If it's concrete you're looking at, the fiber is the rebar, or the metal reinforcement bar, rebar. The matrix is the cement, and then together they make concrete. So you have, in our case, if we're looking at like carbon fiber, for example, on the left you have a sheet of carbon fiber, which is very much like a fabric, the same way you might buy a roll of nylon or cotton, or like bed sheets even. It feels very much like a fabric, and you're adding this resin, and through some certain processes you're able to come up with a really strong part that has way different properties, or you're able to get it in shapes that neither one of these two things could achieve by themselves. So when we look at like a fiber reinforced polymer or plastic, if we look at the fiber, I've seen it spelled both ways, so who knows how it's spelled. So fibers are really good in tension. So you imagine a steel cable or like fishing line even, that stuff is really thin, but you can, when you pull on it, you can apply a fair amount of force before it breaks. But obviously fibers are really poor in compression. So if you ever tried to push something with a string before, you'll find it's essentially impossible. And in general, they're difficult to align and hold in place, especially under loading. So if you're building something out of string, the moment you take away whatever's holding it, they kind of just fall to the floor and don't hold their shape at all. So that's where the other half of a composite comes in, which is the matrix. So this is typically a plastic, hence the term fiber reinforced plastic, normally starting as a liquid. So in this case, I've shown, this is an example of an epoxy where you have its two parts. You'll call it a two-part epoxy. You'll have the resin itself, and then you'll have the hardener. And the two get mixed together and they catalyze, or they react together to form a solid plastic. And in general, plastics, as you know, are probably quite flexible, quite ductile, and they're really good at sticking things together. And because of these kind of properties combining, you can combine these two things to get a quite durable or lightweight piece of material that utilizes both of these properties together. So if we're looking at like composite manufacturing, we have our fiber, we have our matrix or our plastic, but we need to get it into the shape we want it to. So this is part of a carbon fiber bicycle frame, I think. And that's where you follow this kind of workflow that's nearly the same for any manufacturing process in composites, which is you have a mold. So on the right, I've shown a bike frame mold for a carbon fiber bike, and inside the black, that's actually the carbon fiber that will eventually form the part. So you have a mold and you place your fabric into the mold. Next step is you need to get the resin into the fabric. Lastly, you need to secure the fabric into place or hold it to shape. And then finally, you let that resin cure. And then very last step is you pop the part out of the mold and you clean it up a bit and you're done, typically. And this process is nearly the same again for regardless of the process you go with. It's just there's different means to getting these different steps done. So I'm going to cover the three main ways you typically see how to get the resin into the fabric. So if we're looking again at the different steps, placing the fabric in the mold is about the same regardless of how you do it. Either you automate it with a robot, or you're doing it by hand, but either way you're getting fabric and you're sticking it in the mold and aligning it in the direction you want it to. So either do that through a wet layup, through infusion, or through pre-preg. And I'll talk about those more, what those mean. But all these three methods essentially are different ways to get the resin into the fabric. So if we're looking at a wet layup, and sometimes we call this a hand layup, it's similar to paper mache, and that's why I like paper mache as an example, because it's very similar. But instead of newspaper, you've got like your fiberglass, your carbon fiber, and instead of glue, you've got resin. But it's the same idea where you need to get that glue or that resin into the fabric somehow. And we call this wetting out the fabric. So you'll often see, if you're doing it by hand, you'll see a squeegee being used or a little scraper just to scrape the resin over the surface of the fabric until it gets all absorbed. Or you might even use a brush to just kind of paint on the resin until it soaks all the way in. But it's the original way of working with composites, used by traditionally making boats. There's small boats by hand, or model airplanes, let's say. Even some of the original carbon fiber or fiberglass airplanes that were built by hand were done using this method. And it's just because it's so relatively easy and cheap. Again, if you think paper mache, there's a really low barrier to entry. You just need yourself, a mold, some fabric, and some resin, and you can just add the rest by hand. But you can imagine if you're doing this by hand, it works well for small to medium-sized parts. But you've got resin everywhere. It's a lot of manual labor, especially if it's a larger part. You have to squeegee, resin all over this entire surface. And the surface finish itself yields, typically it's okay, but there's other methods that do better. So next we're going to be looking into resin infusion. So it's very similar to a wet layup in the sense that you have a dry fabric. So back to our slide here, you have a dry fabric, you have this resin, and you need to get the two into each other. Both start out with the dry fabric and then a resin that you're adding. But instead of adding it by hand this time and wetting it out with a brush or a squeegee, you're going to use vacuum pressure to pull the resin into the fabric. And I'll demonstrate what that looks like because it's a little hard to visualize. But it's similar to if you take a paper towel and you get one side wet, you'll notice the water kind of pulls its way through the fabric. And it's a very similar process how you'll get the resin to absorb through the fabric, and you'll use vacuum to help pull it through a little bit faster. But yields a excellent surface finish typically because you're using a lot more resin, and all that resin is able to get to the surface of the mold. It's relatively mess-free because instead of having to apply it by hand with a squeegee, it's all done in a bag of sorts, and there's no adding the stuff by hand. And it's pretty good for medium to large size parts. Um, and I'll show you again in the next slide, kind of how big you can really get resin infusion to work. The only con really is that it's a lot more preparation because you need to set up all the consumables. So sometimes you'll see a lot of tubing being used, different flow mediums to allow the resin to actually flow through the fabric in a timely manner. So the setup itself is a lot more, but it's sort of like setting up dominoes. You can, set up dominoes and knock them over one by one, or you can set up a whole string of them and then knock them all down, and they'll just trickle down. And it's very similar to infusion, where there's a lot of work in the setup, but then you pull the trigger and you just make your part in one big shot. So here's a video clip I found on YouTube of resin infusion happening. And this is done on, it's part of a 50-foot yacht, actually. So it's pretty common to see it in airplane parts as well as boats, where it's just too big of a part to do by hand. So what we're doing is that where the dark patches are, that's where the resin's being absorbed into the fabric. And those lines there are either vacuum lines that are pulling the resin through the fabric, or they're supply lines that are supplying resin to the part. And this is the process we used on MS-12 for all the panels. The scale of some of the parts were just too large to want to do comfortably by hand. And we thought it'd be a lot cleaner and give a better finish by doing it through infusion. And then lastly, the last method is pre-preg. So unlike the other two, unlike hand layup or infusion, there's no wetting out of fabric anymore. The fabric actually comes with a resin in it, uncured. So it's pre-impregnated with resin, so that's why they call it pre-preg. So it's really good for getting a really good surface finish. And it has, you get a very lightweight part with a maximum strength because the fabric already has the ideal amount of resin possible. So often one issue is balancing how much resin do you add for how much fabric. Too little resin and it might not fully absorb into the fabric. You might have dry spots, and that's not really good for material properties, nor for surface finish. On the downside, you might add too much resin, and then your part ends up being too heavy and just too much resin overall, because the fabric itself is light, but the resin is quite heavy. It's like a liquid plastic. So having the ideal amount already added to the fabric makes it really easy to get a really strong part for as light as possible. And it tends to be good for like small to medium-sized parts. It can be used for larger parts too, but it gets considerably more difficult, especially with all the equipment required. And that's where you get into the cons, where it's a lot more expensive, mainly because the actual cost of the material itself, you're paying for both the fabric and the resin, and all the work and science that's gone into getting the right amount dosed into that resin. So it tends to be a lot more expensive than raw materials. And then the actual equipment required, typically in a wet layup or infusion, the curing of the plastic can happen at room temperature. Whereas with pre-preg, because of the nature of how you get it, you imagine you don't want your resin cured in the roll of fabric you've just bought. You want it to be uncured so you can cure it when you have it in the mold. So to do that, it comes normally refrigerated or frozen to some temperature well below the activation temperature of the resin. And once you start to warm it up, the two parts of that epoxy resin will mix, they're already mixed together, but they'll start to activate and start to form that solid piece of plastic. But because of that relatively large temperature differential between not curing and curing, often you can't get any that'll cure at room temperature. You need to warm it up to, like, the lowest you get is about maybe the lowest temperature on your oven possible. So essentially like hot air is what you'd want. But if you imagine trying to do that for an entire car, it can be it can be difficult to get an oven that big. And that's what we were struggling with our current car. So with 14, we're using pre-preg for most of the panels because of the excellent properties in both like weight and strength, and the application of using certain cores that allow the part to be even lighter. But the main challenge has been curing the part for something that large and being able to warm it up uniformly and let it all cure at once. And sometimes you need to get it to such a high temperature it requires an autoclave, where you're pressurizing this thing with hot steam and going well above like a conventional oven temperature. And that puts a lot of stress on the mold, let's say, or any other tooling that goes into making a part. But with pre-preg, so it's the one benefit is it's quite easy to add in layers. So this is an example of pre-preg being added. You treat it essentially like a very expensive sticker. So it has a backing layer that you peel off and you stick the fabric down. And it's a lot thicker typically than your typical just the straight up fabric, and it makes it easier to handle and stick into place. And you're able to get stuff placed right where you want it to without it. If you imagine you're sticking pieces of loose fabric around, getting them aligned properly and not falling off the mold can be a bit of a challenge. With pre-preg, you just stick it down like a sticker and then cure it when you need to cure it. So we've talked about, going way back in the slides here, we talked about getting the fabric in the mold, getting the resin into the fabric. But we're going to also talk about is how do you hold that fabric in place to get it into the right shape. So you can imagine if you have it on some funky shape of a mold, if it starts to uncrease itself, if you're trying to force this fabric into a really small crevice, but it just doesn't want to stay down there, you can imagine when you pull your final part out, it won't actually conform to the mold properly unless you have something shoving it into that crevice. And typically, even on any flat sheet, you still want something to hold down your fabric. And what we tend to use is vacuum bagging. And what that is you're using atmospheric pressure to help suck, or you're sucking air out of a bag and allowing atmospheric pressure to push the fabric against the mold. And the reason you do this is because vacuum pressure is actually really powerful. So atmospheric pressure is 14.7 psi, so or pounds per square inch. So if you were to suck all the air out of something that was 1 inch by 1 inch, you'd actually be placing the equivalent of 14.7 pounds on top of it. So if you imagine scaling that up for a part that's several feet large, or a foot by another foot, to get that same amount of clamping force in just using weights, you're looking at whatever 12 times 12 times 14.7, so many hundreds of pounds to the same amount of force that you can use with vacuum. So to do that, typically there's two methods to get your part vacuum bagged. Either you do something called a surface bag, so that's on the left here, where you've got, if you can see, there's a mold, they've got a flat sheet in this example. You have tape that secures this bag, this vacuum bag, to the surface of it, and then you're sucking out all the air and causing that part or the bag to get sucked against the part and then squish it against the mold. So that's one method. And the other method is something called envelope bagging, and that's where you make a bag, like literally an envelope out of your vacuum bag film, and you're sucking the air out of that. And so it's very similar to if you've ever used like a vacuum sealer for food. That's essentially a vacuum envelope bag where you're sucking the air out and the bag's just being sucked against the food. But both these methods work. You can imagine that for a really big part, it might be hard to get an entire part, like an entire bottom half of a car, into a mold or into a bag. And that's where using a surface bag is a lot more feasible. But in general, it can be easier for smaller parts to put them in a bag and suck all the air out than trying to tape up a nice surface bag onto it and suck it down without having any leaks. So the last thing I was going to talk about is molds a bit. So the biggest kind of limitation when you think about molds, so it's really easy if you have a mold already and you're just laying fabric and vacuum bag and calling it a day. But when you're making your own custom shape, that's where you have to go make your own mold. And the biggest stresses, I guess, on any mold is that it needs to hold up to vacuum pressure. So being able to get squished by vacuum and not break or get crushed. It needs to not stick to any resin or fabric you're applying to it. And if you're heating it up in an oven, or at least subjecting it to relatively warm temperatures, you need it to not start to warp or deform or even melt under those temperatures. And there's a variety of ways to do this. This is where I ran out of time on slides. But for our car, for example, we're using MDF molds, so layers of wood that have been machined. And we're using glue to hold those layers together. Other applications you'll sometimes see is instead of machining a mold. So one difficulty with machining a mold is the cost associated with that. To get things CNC machined typically costs a fair amount of money. And if you're making something rather large, it's just a lot of machining time that goes into making that mold. So one way you can get around this is to make or use an easier to machine material. So like styrofoam, for example. But you can imagine styrofoam really isn't a great mold material by itself because it's not very resistant to vacuum pressure. It'll just get crushed really easily, and it'll become very easily destroyed by being stuck to the composite part. So typically you'll use something called a plug in a mold system, where you're making you're making a model of the part you want out of an easily machined material. So if I'm making a cup, for example, I'll make the cup out of styrofoam first, and then I'll make a mold off of this. We call it a plug or a pattern. We'll make a mold out of a more resilient material, but instead of having to machine it this time, we can actually make that mold out of composite and not use such an aggressive process. We can not use vacuum bag, or we don't need to vacuum bag it. If we don't need such a good conformance, let's say, we can normally wet it out by hand with a wet layout procedure and still make a mold. And then from there, use that new toughened whatever composite mold we just made as the actual mold for the final part. And then lastly, in our last kind of closing few minutes, one thing I wanted to talk about was, I guess, sandwich panel construction. So sandwich. The idea is you have layers of different materials staggered to provide different material properties. And the one thing that often gets overlooked is the thickness of the panel. And thickness plays a really important part in the strength and the stiffness of a panel. And a really good example of this is if you look at corrugated cardboard, for example, where you have layers of whatever cardboard like paper on either side of this grid shape core, it's way stiffer than just peeling off the outsides and flexing them. They're essentially just paper. And the reason for this is you're loading the top surface. If you're bending it downwards, you're loading the top surface in tension and the bottom surface in compression. And the further out you space these layers, the stiffer it will get. And if you're in mech or Tron, you'll learn about deflection and material properties. But essentially, the modulus of or moment of inertia for any rectangular shape, it'll be the thickness of it to the third power or cubed. Will be it's proportional to the stiffness. So if you double the thickness of a panel, you're actually making it 8 times stiffer per se. Around there, you can check my math, but that's about the math you tend to use. So often you're using a core material to space out your layers of composite on either side to get a stiffer part, rather than make it out of solid carbon fiber or solid fiberglass, where you end up getting a lot heavier of a part for similar properties, mind you, maybe way overbuilt. I guess lastly, so in terms of resources, a lot of this stuff can be found online in terms of how to do these different processes. I absolutely love Easy Composites. They're a YouTube channel. They also have a website where they actually go over how to make these parts using these different techniques. So if you ever are curious, I'd always try and find the first Easy Composites video that's relevant to that topic. Otherwise, in terms of websites, Explore Composites was another website I found that was pretty handy in terms of being just an online resource with web pages dedicated to the different processes. But if you have the time, again, I really recommend watching a video on how to do it, where you actually see the process being done, as opposed to someone trying to describe to it how to do it in words. And then my last resource I've listed is Composites Canada, and they're just a warehouse and a vendor we use. They're located in Mississauga. They have a pretty okay looking website that's relatively easy to navigate, but they provide a really great student discount for us, and they're relatively local as opposed to having to get them shipped across Canada, let's say, or even from the US. So when we ever try and do composites, we always check Composites Canada first to get a rough idea on pricing. And if possible, we'll end up buying from them just to get a price discount and just to get it in a relative short amount of time. So that's all I have covered. It is officially 10 p.m., but I'm happy to answer any questions at this point, if anyone has anything on what I've covered so far. But I will share the slides and also the recordings and post in the appropriate Slack channels where all the stuff will live. But any questions at all? Sweet. I'm going to take that as a no. If you ever have any questions, always feel free to like message me. But you'd be surprised how much resources there are online about any of this stuff. So definitely, check out these resources first, or just do your own Google searching to see what's out there. As far as interiors, where I see a lot of this stuff happening. So if we're looking at catamaran cover, most like we're wholeheartedly going with composites for this construction. One of the big, I guess, downfalls I didn't cover on here, or pitfalls of carbon fiber, although it's very stiff and very light, it's electrically conductive. So I know that we were talking about using fiberglass instead, because fiberglass is more of an electrical insulator than a conductor. And surprisingly, the actual properties between fiberglass and carbon fiber are relatively similar. Carbon fiber, although it's quite hyped up and it's a thing that we all like to see for expensive products, they're both relatively similar. The only difference being that carbon fiber tends to be stiffer for its own weight, so it's a higher stiffness to weight ratio and potentially a higher ultimate strength. But overall, there isn't a major difference aside from the look you get and the slight weight reduction you get with carbon fiber. And carbon fiber tends to be moderately more expensive than fiberglass. So depending on the application, it's totally reasonable to switch to fiberglass as opposed to carbon fiber. So I guess in terms of catamaran cover, we'd be looking at, if we're needing stiffness, let's say, it's adding the right amount of core in the right areas such that it's stiffer where it needs to be stiff. And the nice thing about composites is that you don't necessarily need to make the entire thing uniformly thick. You can only put core where you need it and use a thinner core somewhere else or use less core somewhere else, where it's easier to fit into a corner, let's say, where it might be hard to get a really thick core to follow a really tight corner. When we're looking at other parts of the car on the interior side, so the interior door panel, there's a large, well, we'll most likely need to use composites in that too, just for the strength and the rigidity that composites brings, as opposed to just using foam core, let's say. With that, we may not need such a thick core. We might not even need a core because it doesn't necessarily need to be subject to so much loading. It may act more like a glorified cover than a really strong panel that'll take a lot of impact or loading. And then for seats, most definitely that will be composites again. And a similar idea where it'll be looking at how do we add core in the right spots to provide the right amount of stiffness, but also maybe not using core in certain areas if we need to fit it into a tighter corner. And I guess for any of these three applications, we'll need custom tooling of sorts. We'll need to make molds for these panels. And we're still kind of in the preliminary stages of what mold we go with or how do we make our molds. Only word of advice, as well as the process we go with, whether it be wet layup, infusion, or prepreg. I would probably recommend, if possible, for depends on the size, I guess. So the one difficulty again with the whole prepreg situation is the whole oven needing to bake the part. Whereas with wet layups, so infusion or wet layup, those can happen at room temperature. Depending on if we do some math to figure out the weight of the actual part, if it's a relatively small part, it may not make a lot of sense to use prepreg. If it's just as easy to do with a wet layup. For the seats, let's say, we may want to look at considering prepreg, just based on how big it is and maybe there's some room for weight reduction. But we may also want to consider all the other options too. As far as, and then for catamaran cover, we'd be in a similar boat. My only gripe with any prepreg process is that the mold itself needs to be fairly resilient. So for machining MDF, for example, it means that we need to have the ability to machine this stuff. So hoping that next term we have that availability, but there's a risk we might not. And we wouldn't want to have, a mold that costs us way more money to make than the part actually brings value to the car. And that's where we might look at using styrofoam that could be manufactured by hand even, or manufactured by another vendor for a lot less money. And going with another process that's more attainable, like a wet layup or infusion process. But there still needs to be probably a big discussion on the actual process we go into for each of the different components of the interior. Yeah, I think that's all I've got, at least on the interior side. I'm happy to call it here, unless anyone else has any dying questions at the moment. If not, I will end this call and then post these slides again, interiors wise, as well as maybe in the Met Class of S 2020 channel, and then I'll also be uploading this recording down the line. But hopefully you found this as a brief kind of intro to how we do composites and the different methods that are out there. And next steps, I'd highly recommend checking out some of those videos again by Easy Composites, at least getting an understanding of the process and how they make their molds or how those different processes work. Yeah. Any dying questions at all? Fascinating. Okay, we'll end it here then. Thank you, everyone. Look forward to, I guess we'll be following up with one of the interiors reviews, but we'll start a new call for that. So have a great evening, everyone else. See you around. Thank you.
Thanks for coming.
Thanks for attending my TED
Thank you,
Talk.
Adrian. Have a good night.
See ya.